Welcome back. For 6 episodes, the star has been the vector, an arrow, a list of numbers, a row of data. Today we meet the object that acts on vectors, the matrix. At first glance, a matrix is nothing but a rectangular grid of numbers laid out in rows and columns, and the first operations on it are easy. You can add 2 matrices, you can scale one by a number, and you can flip one across its diagonal to form its transpose. We will get those out of the way quickly. Then we reach the idea that makes the whole subject run. When a matrix multiplies a vector, the answer is a linear combination of the columns of the matrix. That one sentence is the secret engine of linear algebra, and once you see it, systems of equations, transformations, and inverses all click into place. We will also meet the identity matrix, the matrix that does nothing, and the dimension bookkeeping that tells you when a product is even allowed. Let's begin. Let's pin down the object. An m by n matrix is a rectangular array of numbers with m rows and n columns. We always say rows first, columns second, so a 3 by 2 matrix has 3 rows and 2 columns. The entry in row I and column j is written with a lowercase a and 2 subscripts, I then j, so a12 sits in the first row, second column. The size, also called the shape, is the pair m by n. Some special cases name themselves. A single column is an m by 1 matrix. That is just a column vector, which means our vectors were matrices all along. A single row is a 1 by n matrix, and when the number of rows equals the number of columns, we call the matrix square. Square matrices are special because they can act on a space and return to the same space. You can read a matrix 2 ways, as data, like a spreadsheet of numbers, or as a machine that transforms vectors. Both readings will earn their keep, and the rest of the episode builds the machine. The 2 easy operations come first, and they behave exactly like vectors. To add 2 matrices, they must be the same size, and then you simply add the entries in matching positions. So the entry in row 1, column 1 of the sum is the sum of the 2 entries in row 1, column 1, and so on across the whole grid. You cannot add a 2 by 2 matrix to a 3 by 3. The shapes have to match. Scalar multiplication is just as direct. To multiply a matrix by a number, multiply every single entry by that number. 3 times a matrix triples each entry. These operations obey all the familiar laws. Addition is commutative and associative. Scaling distributes over addition. The zero matrix full of zeros is the additive identity, and negating every entry gives the additive inverse. In fact, the collection of all m by n matrices with these 2 operations is itself a vector space, exactly like Rn. Addition and scaling are the boring part. The interesting structure is the product, and that is where we head next. The third simple operation is the transpose. The transpose of A, written A transpose, flips the matrix across its main diagonal, the diagonal running from the top left corner down to the bottom right. Concretely, the entry that sat in row I, column j, moves to row j, column I. Rows become columns and columns become rows. So a 2 by 3 matrix transposes into a 3 by 2 matrix. The first row, 1, 2, 3, stands up to become the first column. A couple of clean facts. Transposing twice brings you back to where you started, so the transpose of A transpose is just A, and the transpose of a sum is the sum of the transposes. One special case deserves a name. If a matrix equals its own transpose, so that the entry in row I, column j, always matches the entry in row j, column I, we call it symmetric. Symmetric matrices must be square, and they turn out to be the best behaved matrices in all of linear algebra. They run the second half of this course when we reach eigenvalues and the spectral theorem. Now the heart of the episode. When a matrix A multiplies a vector x, what do you actually get? Here is the viewpoint that unlocks the whole subject. Think of A as a row of columns standing side by side, the first column, the second column, and so on. Then A times x is a linear combination of those columns, where the weights are the entries of x. The first entry of x multiplies the first column, the second entry multiplies the second column, you add them all up, and that sum is the answer. Watch the example. The 3 by 2 matrix has first column 1, 3, 5, and second column 2, 4, 6. Multiply it by the vector 10, 20. The result is 10 times the first column plus 20 times the second column, which gives 50, 110, 170. There is also a row recipe that gives the same answer. The ith entry of A times x is the ith row of A, dotted with x. The row recipe is handy for hand computation, but the column viewpoint is the one to remember, because it explains everything that comes later. Why is the column view such a big deal? 3 reasons, each a pillar of the course. First, systems of equations. A system with coefficient matrix A, unknown vector x, and right-hand side b is exactly the single equation A times x equals b. And because A times x is a combination of A's columns, solving the system asks one geometric question: can B be built as a combination of the columns of A? Second, a matrix is a function. The rule that sends x to A times x is a linear transformation from Rn to Rm. It respects addition and scaling, so matrices are linear functions in disguise. Third, and most beautiful, if you feed in the standard basis vector with a 1 in slot j and zeros elsewhere, you get back exactly the jth column of A, so the columns of A are the images of the coordinate axes. To know a linear map completely, you just need to know where it sends the axes, and those destinations are the columns. One special matrix deserves its own slide, the identity matrix. The n by n identity has ones running down its main diagonal and zeros everywhere else. Its defining property is that the identity times any vector x returns that same vector x completely unchanged. The column viewpoint explains why instantly. The columns of the identity are precisely the standard basis vectors. The first column is 1, 0, 0, the second is 0, 1, 0, and so on. So the identity times x is x1 times the first basis vector plus x2 times the second, and so on, which just reassembles x itself. The identity is the do-nothing transformation, feed in any vector, get it straight back. It plays the role for matrices that the number 1 plays for ordinary multiplication, and we will lean on it constantly. In particular, 2 episodes from now, the inverse of a matrix will be defined as the matrix that multiplies A back down to the identity. Hold on to the identity, it is the anchor. Before we compute, one rule of bookkeeping that you can never skip: conformability. A times x is only defined when the sizes line up correctly. Write A as m by n and write the vector x as n by 1, since x has n entries stacked in a column. For the product to make sense, the number of columns of A must equal the number of entries of x. Both are n here, so it works, and the result A times x is an m by 1 vector. It has m entries. Picture the two size labels written side by side, m by n, then n by 1. The inner numbers, the two n's, must match, and when they do, they cancel, leaving the outer numbers, m and 1, as the size of the answer. If they don't match, say a 2 by 3 matrix meeting a vector with only 2 entries, the product is simply undefined, there is no answer to compute. This inner matches, outer survives rule looks small now, but it returns at full strength next episode when we multiply a matrix by a matrix. Let's make the column viewpoint visual. On the grid, the two columns of a 2 by 2 matrix A leave the origin as 2 arrows, the first column in blue, the second column in orange. Now the vector x supplies the weights. Its first entry is 2, so we double the blue column. Its second entry is 1, so we take 1 copy of the orange column. We lay them tip to tail. The doubled blue arrow first, then the orange arrow starting at its tip, and we land at a final point. The bold green arrow from the origin to that point is A times x. Stare at this picture because it is the whole idea in one frame. A times x is never mysterious. It is a weighted blend of the columns of A, with the weights read straight off the vector x. Change x, and you slide to a different blend. The set of every blend you could possibly reach is the span of the columns, the theme that opened this course and that the matrix now makes concrete. Here is the transpose as a picture. On the left sits a 3 by 2 matrix, its entries labeled by row and column. The dashed line is the main diagonal running from the top left corner downward. To transpose, imagine folding the matrix across that diagonal like a hinge. The first row swings down to become the first column. The second row becomes the second column. The third row becomes the third column. What was 3 rows of 2 entries becomes 2 rows of 3 entries, a 2 by 3 matrix. Follow a single entry to feel it, the number sitting in row 2, column 1, moves to row 1, column 2. It crosses the diagonal to its mirror position, row and column subscripts simply swap. If the matrix happened to be symmetric, that fold would land every entry exactly on top of an equal one, and the picture after folding would look identical to the picture before. That visual symmetry is precisely what the word symmetric means. Let's run the easy operations together. Take A with first row 1, 2, and second row 0, 3, and take B with first row 4, -1, and second row 2, 5. We want 2A minus B. First scale, 2A doubles every entry of A, giving first row 2, 4, and second row 0, 6. Now subtract B entry by entry. Top left, 2 minus 4 is -2. Top right, 4 minus -1 is 5. Bottom left, 0 minus 2 is -2. Bottom right, 6 minus 5 is 1, so 2A minus B has first row -2, 5, and second row -2, 1. Now transpose that result. Rows become columns, so the first column, -2, -2, stands up as the first row, and we get first row -2, -2, and second row 5, 1. A nice check, you can transpose first and combine afterward, and you will get the very same matrix because the transpose respects addition and scaling. The easy operations commute with each other in exactly the way you would hope. Now the matrix vector product, computed both ways so you trust they agree. Let A be the 2 by 3 matrix with first row 2, 0, 1, and second row -1, 3, 4, and let X be the vector 1, 2, -1. First, the column view, the one to remember. A has 3 columns, 2, -1, then 0, 3, then 1, 4. We weight them by the entries of x, 1 times the first column, plus 2 times the second column, plus -1 times the third column. Adding the first components, 2 plus 0 minus 1 is 1. Adding the second components, -1 plus 6 minus 4 is 1. So a times x is the vector 1, 1. Now the row view as a check. The first row dotted with x is 2 plus 0 minus 1, which is 1. The second row dotted with x is -1 plus 6 minus 4, which is 1. Same vector, 1, 1. And the sizes work. A 2 by 3 matrix times a 3 by 1 vector gives a 2 by 1 vector. Both recipes, one answer. Last example, in 2 parts, both showing the column viewpoint pay off. Part A, confirm the identity does nothing. Take the 3 by 3 identity times the vector 7, -2, 5. By the column rule, that is 7 times the first basis vector, minus 2 times the second, plus 5 times the third, which simply reassembles 7, -2, 5. The vector comes out untouched, exactly as promised. Part B shows how to read a transformation off its columns. Take a diagonal with 2 and 3 on the diagonal. Feed in the first basis vector, 1, 0, and you get the first column, 2, 0. Feed in the second basis vector, 0, 1, and you get the second column, 0, 3. So A sends the first axis to twice itself and the second axis to 3 times itself. Without computing anything else, we already know A is a scaling transformation. It stretches the horizontal direction by 2 and the vertical by 3. The columns told us the whole story of the map. A short history. The idea of arranging coefficients in a grid and operating on them is ancient. The Chinese classic, The 9 Chapters on the Mathematical Art, from around 200 BCE, already solved systems of equations by manipulating rectangular arrays of numbers, elimination, centuries before anyone wrote it as algebra. The modern story starts in the 1800s. In 1850, James Joseph Sylvester coined the word matrix, borrowing the Latin word for womb because he thought of the array as the womb from which determinants are born. Then in 1858, Arthur Cayley wrote A Memoir on the Theory of Matrices, the paper that treated matrices as objects in their own right. Cayley defined addition, scalar multiplication, and crucially the matrix product as operations you could do algebra with, not just bookkeeping for equations. Later, Ferdinand Frobenius and others built the deep structure theory, rank, canonical forms, and more. Matrices were born as a tool for equations and grew into one of the central objects of mathematics. Let's recap. A matrix is a rectangular grid of numbers, sized rows by columns, with the entry in row I, column j written AIIJ. You add 2 matrices of the same size entry by entry, and you scale a matrix by multiplying every entry by a number. The set of all matrices of a given size is itself a vector space. The transpose of A swaps its rows and columns. Transposing twice returns the original, and a matrix that equals its own transpose is called symmetric. The centerpiece was the matrix vector product. A times x is a linear combination of the columns of A, weighted by the entries of x. That single viewpoint pays off 3 ways. A system of equations is just A times x equals B, a matrix is a linear transformation, and feeding in a basis vector reads off a column. The identity matrix has 1s on its diagonal and returns every vector unchanged. And conformability is the bookkeeping rule. To multiply, the inner dimensions must match. Next episode, we let one matrix act on another, and the product turns out to be the composition of transformations. Today, we met the matrix. A matrix is a rectangular grid of numbers with a size we write as rows by columns, so a 3 by 2 matrix has 3 rows and 2 columns. We add 2 matrices of the same size by adding entries and matching positions, and we scale a matrix by multiplying every entry by a number. The transpose of A, written A transpose, flips the matrix across its main diagonal, turning rows into columns. The entry in row I, column j, becomes the entry in row j, column I. Then came the heart of the episode, the matrix vector product. When the matrix A times the vector x is computed, the result is a linear combination of the columns of A, using the entries of x as the weights. So A times x is x1 times the first column of A, plus x2 times the second column, and so on. This single viewpoint is the key to everything that follows. The identity matrix has 1s down its diagonally and 0s elsewhere, and the identity times any vector returns that same vector unchanged. Finally, dimensions must be conformable. To form A times x, the number of columns of A must equal the number of entries of x. Next episode, we let one matrix act on another and discover that matrix multiplication is the composition of transformations. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.